Welcome to Hacking the Pandemic's most popular software, Zoom. When the pandemic forced everybody to work from home, we all bravely installed software we never heard of before. Everybody remembers those meetings where children were running around in the background, cats jumping suddenly in front of the camera, and phrases like, "You're on mute," or "Can you see me now?" Sharing your company's secrets online has never felt more comfortable. I'm Thijs Alkmaar. I'm part of the research department at Computest, and I did this research for Zoom with Daan Kuiper. We are a security company in the Netherlands, and we mainly focus on pen testing, and we have an incident response department. And Daan and I are the research department, which is called Sector 7. We do research in the public interest, so research that hopefully can make the world a little bit safer. And that's also something that we will be talking about today. In spring this year, we demonstrated a zero-day attack against the Zoom client during the Pwn2Own competition. During this competition, we demonstrated that we could take over the computer running the latest version of Windows and with the latest version of Zoom through communication via Zoom without any interaction by the victim. This was the results of 2 months of research. And we started this research soon after the announcements of the targets of the Pwn2Own competition this year. So Zoom was included for the first time, actually. Because of the pandemic, CDI, the organizer of the competition, thought that these enterprise communications apps had suddenly become way more important, and therefore that they also should be included for this competition. Now first, how did we approach our research? Now, these are basically the general steps that we followed during our research. So just for finding those vulnerabilities. First of all, when we started, we hadn't really used Zoom much. We mainly used Microsoft Teams. So the first step was just trying to figure out where all of the features are, everything that you can do or send through Zoom to somebody else, and try to make a list of that. So there's many people know it for the meeting functionality or for sharing your screen, but you can also chat, and there's even a chat outside of meetings, which has a lot of features like group chats, sending images, stuff like that. And our goal was to really make sure that we know everything that you can send to somebody, because that was part of how the attack had to work. We had to send something to somebody and take over their computer. And then the next step was getting network interception. So this was foreseeing what would actually be transferred if you try to use those functionalities that we found in the previous step. And then with that, we could try to understand the parts of the design, how is everything implemented, and in which part of the application is what being handled. And then we looked at what are the interesting areas in the application. Where do we think we are going to find these vulnerabilities that we can use? And finally, we then started reverse engineering those until we found a vulnerability that we could use. So Zoom actually has multiple different protocols which it uses. There's the out of meetings chat, which uses XMPP, which is an open standard for chat functionality. There's some HTTP API for specific operations like logging in and stuff like that. And then the meetings themselves, those use a custom binary protocol. It's typically UDP based, but it can fall back to TCP. And of these, we decided that XMPP would be the most interesting for us, because by design, XMPP allows you to send basically arbitrary XML to another user. And the server really enforces very little on what that contains. It's also much easier to reverse engineer than the meeting protocol, because XMPP is an open standard. You can just read the standard and compare it to what Zoom does. While the meeting functionality or that binary protocol would have taken a lot more time to reverse engineer. So we decided to focus basically on the XMPP part. And now for the good stuff. What vulnerability did we find? So, as I said, we defined some areas of interest. So what type of vulnerability do we expect and where do we expect it in the application? Now we needed to take over that remote computer. And because Zoom is developed in C++, we thought the most likely method would be some form of memory corruption. Now, this could be a buffer overflow or use after free or something like that. And we thought, well, these buffer overflows are not very likely if you use C++ correctly, if you use this string objects from C++. And in addition, all of the XML, as I said, goes through the server. There's no direct connection between users if you are chatting, which means that a parsing vulnerability is not very likely here because, well, the server also has to accept it and pass it on. If it's not valid XML, then the server will just reject it and not forward it to the other user. So we had this idea of looking for calls to OpenSSL. Now, Zoom contains a number of libraries, some open source, and one of those is OpenSSL. And this is a library written in C, which means that if you want to use it from C++, you will often need to convert between standard objects in string objects in C++ and C buffers for the OpenSSL functions. And also because it's open source, we have documentation, we have the actual implementations that we can look at. So it's much easier for us to understand what the OpenSSL calls are doing than just reverse engineering the entire application. And there was this early on, there was already a hint that maybe this would be an interesting thing to look at. So we noticed this in the decompiler. So basically what you see here is a function for calling the base64 decoding from OpenSSL. It takes a string object from C++, it allocates a new string for the result, and then it passes the string or the pointer to the buffer to the EVP decode block function. If you look carefully at the lengths here, you'll see that it creates a new buffer that is 4 times as large as the input. So the length is shifted twice to the left, which means multiplying by 4. But base64 decoding, this actually reduces the length. It takes something text-like and reduces it to something binary. So it always about 3/4 of the size of the input. So this was a first good hint that this OpenSSL functions and mainly the conversion between strings and C-style buffers, that this would be an interesting area to look at for us. And then I looked at the advanced chat encryption of Zoom. So there's this setting, it's named advanced chat encryption, that you only have it if you have a paid account, and you must enable it on the website. So I think it's a very not well-known setting. And it's also, if you enable this, then your chat messages are encrypted and a lot of the features no longer work. So I think maybe sending an image to somebody, stuff like that no longer works. And what I noticed in the implementation is that there's basically 2 versions of this protocol. There's an older version 1 and there's a version 2. And they have been around for a couple of years. So if you look at this together, then you see here some conversion between C and C++. There's using the OpenSSL API. It's a hidden or less well-known feature, and also an older protocol version. If you combine all of that, then this just makes it a very interesting target for us to reverse engineer to look for vulnerabilities. Because all of this combined makes the chance of a vulnerability quite high, and it could also have a lot of impact. So here's the plan for reverse engineering this. So I looked at places where OpenSSL is called with a buffer, and then I traced from where that buffer was created to where it was used to see what the length of it could be, what checks are there on the length, and is it user input or not. And this often goes through multiple different steps, or maybe some conversions first or string operations first. I was also trying to identify which of those variables are actually controlled by something from another user. So there's a lot of functionality in Zoom you cannot call as another user, but but I was focusing on trying to find where you can send something, for example, through a message. And then the second step was trying to find where these are being called. So is there really something is this function actually ever called? There's a couple of functions that could be vulnerabilities, but they were just never used. And then eventually I found something that worked. So going back to that advanced chat encryption, if you send an encrypted message in a new chat with somebody, then it basically follows the following steps. So you send this message, which is encrypted with a new symmetric key. I'll call that the message key. And it also gives it an identifier, so a key ID that indicates with what key the message was encrypted. Now, when that receiver sees a new message which is encrypted and it doesn't have the key associated with that identifier, then it will request that from the sender. And by requesting that, it also includes its X509 certificate, which we'll call the identity key. And then the sender of the message responds with a response key message. This contains that message key, and it is encrypted and signed using the identity keys of both the sender and the receiver. And here there are, again, two options. So the result of the decrypted key is placed into a buffer with a size of 1024 bytes. And there's two options here. So this depends on the certificate of the user. It can use RSA with an RSA key. And in this case, the bounds are properly checked. So before copying it to that 1024 byte buffer, it checks if it will fit. There's also a variant which uses elliptic curve. And if there's an elliptic curve key, and then it uses elliptic curve Diffie-Hellman to compute a shared secret, which is used for AES. And then there's no check on the size of the ciphertext. So if you send a response key message with a ciphertext that would decrypt to more than 1024 bytes, then this would overflow that buffer and therefore overwrite other memory contents. For exploiting this vulnerability, there are a couple of pros and cons for how this buffer overflow works. So first of all, it is arbitrarily large. There may be some limits based on the size of an XMPP packet, but that in practice, that's way more than you need, which is very useful because we can make it as long as we want. There's also no limitations on the character set, so it doesn't need to be valid XML because it's decrypted and also base64 encoded before it is sent. And the nice thing about it for the competition is that you could trigger it using chat messages without interaction of the user. The user didn't need to click on anything. We just send this message, the user's client automatically responds to retrieve the key, and then we can trigger the buffer overflow. But there are also some cons that make it more difficult for us. So the size of the allocation of the buffer that we overflow, it's a heap allocation, and it has a fixed size of 1040. So there's a little bit of overhead for these string objects. And the overflow size has to be multiple of 16 because the AES block size is 16. So we always need to overwrite something that's a multiple of that. And then the most tricky one of these is the last one. So this buffer is allocated and then it triggers the overflow when handling just one message. So often to make a reliable buffer overflow into an exploit, what you do is you place the object to trigger, or you trigger the overflow from, then you place something after it. And then maybe you can even check if the layout is correctly, and then you trigger the buffer overflow. But in our case, the buffer would be placed and then overflown with just one message. So we had to make sure that whatever we wanted to overwrite is already there in memory. And this proves pretty tricky with how the heap allocator works in Windows. I'll talk about that later. Now, to make this exploit reliable, we also relied on two other vulnerabilities. The first one, so as I said, that XMPP has to pass through the server. And this means that we are very limited in how we can basically interact with the remote client. So, for example, we can make sure that the client does some allocations, but through the server, it was tedious to get this to work well. So we had this idea of, can we somehow trick the Zoom client into making a connection to us? Eventually, we found a way, although we're still not quite sure why this worked, but it did. And it uses the marketplace functionality of Zoom. Zoom has a marketplace, which has apps. You can basically think of these as chatbots that you can add to your account. And when you add a new chatbot to your account, then Zoom needs to download the image associated with that chatbot, a logo for that user. So, for example, SurveyMonkey has a marketplace app, and then the server sends to the Zoom client, hey, there's a new marketplace application, here's the image for it, go and download it. And then Zoom will start downloading that image. And how that works is that it always downloads it from marketplacecontent.zoom.us. So in this example, it would download this path from the server. But what we noticed is that we could do this instead. Now, instead of something under zoom.us, this is now a domain containing .computest.nl, which means that it is a server of us that it starts connecting to. And when we tried this, we saw an incoming connection on our server. Now, this was very useful for our information leak, which I will talk about later. First, the second minor vulnerability that we used. This one is even lower impact than the other one. We needed some way to fill up the memory of the Zoom process with data that we could specify. I'll talk about why later. And what we found is that if you send an image to Zoom, then that image is automatically downloaded and shown in the chat. If it is with below a specific size, it's a couple of megabytes, I don't know the exact size. But if you send a GIPHY link to somebody, so a GIF file from GIPHY, then it is downloaded regardless of the size. So there's no size check there. Now, what we could do is that we could upload our own GIF file and then use path reversal to make the client think that it's downloading a GIPHY file, but instead it is downloading a GIF file we created containing our data. And we can make this arbitrarily large and therefore fill up the memory. Now for getting to exploitation. So far, it took us about a week and a half to find this buffer overflow. So this was quite soon for finding a vulnerability like this. But then we had to build a complete exploit, so something that could perform the full attack during the competition. And this took us another month and a half to make it reliable enough to use during the competition. To give some more background on us, both Dan and I had zero experience with memory corruption on Windows. We have a lot of experience with macOS and Linux, but Windows, we didn't know much about it. We had to read up on everything, so not just on Zoom, but also what debuggers do people use on Windows? How does the Windows heap allocator work? What are the system libraries that you can use? The calling conventions for 32-bit Windows applications. All of these things we had to study during this research. If you're more experienced with Windows, then this would probably have taken a lot less time, but eventually we also succeeded in this. Now, our exploit has basically 4 steps. These are basically the same as for many vulnerabilities that cause memory corruption. I'll go through them one by one. So first of all, heap grooming. Now, the buffer is allocated on the heap. And as I said, if we trigger the buffer overflow, then, or if we trigger it, then it will automatically overwrite what is after the buffer in memory. But if you just try it without any preparation, then it could be basically anything could be in memory there, which means that there's a large chance that the application crashes if we just overwrite something in memory. So heap grooming was really about making sure that we know what is after this buffer in memory. This is a very important step for reliability, and it took a lot of time to get this reliable enough, because we would often just overwrite something incorrectly and then trigger a crash of the application. So how does the heap work under Windows? Well, Windows has two different implementations for heap in user space applications. So there's for all the applications, there's an NT heap, and there's a new segment heap, but this one is opt-in and only used by specific applications like Edge or the most modern applications. So we focused on the NT heap. Now, the basic functionality of the NT heap is as follows. They have a list of memory which is free in a sort of like a linked list. And this list is sorted by size. So it starts with the smallest one and then it goes up. So if you request a specific size, then it can start on that list and then it looks at that list until it finds one that fits and then returns that to the application. And when something is deallocated, then it is combined with what is before or after it, if those are also free. Now, there is another implementation. So if there are 17 active allocations for a specific size, then from that moment on, allocations of that size will be handled by the low fragment heap. So this is a different type of heap implementation. The low fragment heap is used for, as I said, for something that's a 17, so therefore for common allocation sizes. So multiples of 2 or powers of 2 are often handled by the low fragment heap. And also, once something is handled by the low fragment heap, there's no way to go back to the normal free list for that size, even if the 17 active allocations are deallocated. And how the low fragment heap works is that it groups together similar sizes into a bucket. And then when there's a new allocation, it looks at the bucket and it picks a random slot from the bucket that is still free. This randomness is exactly to make these vulnerabilities like this harder to exploit. That means that exactly grooming the heap, so making sure that you control everything where it is, this is just impossible on the low fragment heap. And also a common recommendation for exploiting heap vulnerabilities in Windows is to make sure that you're on the free list and not on a low fragment heap. Originally, we had this plan. We had to overflow a buffer of 1040 bytes. We first tried to make sure that that free list was in the state that we wanted by sending messages and deleting messages. So you can revoke a message, which then means that that memory is again deallocated. So in this way, we could make some modifications to how the heap worked. So we could send a lot of messages to fill up specific free memory areas to make sure that the layout was as we wanted it. But doing that with enough precision to make this work was very difficult. We ran into a couple of problems. One of those is that every time you send a message, it needs to pass through an XML parser and then it's copied a couple of times. So this basically means that it is very easy to accidentally trigger the LFH for a specific size. And if that's a size that we need for our exploit, then the attack will fail. And more importantly, even that size that we needed, a couple of times, every couple of runs, that 1040 was already being handled by the LFH after we freshly started the application. So we hadn't sent anything yet, but by the other communications that the application does, the 1040 was already handled by the LFH. And this was pretty bad for our exploit because it meant that there was a certain chance that our attack would be impossible even before we started. So we spent a lot of time on this. We tried to make this work as reliable as possible, but eventually we had to give this up and we formulated a new plan. Now, in this new plan, we directly forced that 1040 to the LFH, which we can just do by sending 17 messages, and then try to do our exploit there. So this automatically gets to the next problem. Now that LFH is random, how do we make sure that we overwrite what we want? Well, the more important thing is, how do we make sure that we don't overwrite something that will cause the application to crash? And then we used the following method for that. So first of all, we wanted to make sure that the application would not crash. This was the most important thing. And if we launch the application, there will be some things in the bucket already there that we do not want to overwrite. These are indicated in orange here. And what we could do is send new messages to it, indicated in green, that would slowly fill up this bucket, and then another one, and then start a third bucket. And then we would again delete some of those messages, but making sure that we kept the very last one. So we would end up with a layout which looks something like this. Now, in this case, if we would do a new allocation, those would happen in bucket 3, which has a lot of room available for us. So there are no unsafe objects here, and we have a lot of free slots that we can use for performing our exploit. The next step is the information leak. So why this is needed is because of two mitigations known as ASLR and DEP. ASLR is address space layout randomization, and DEP is data execution prevention. These are exploit mitigations in Windows, and many other operating systems have something similar. And ASLR means that the place of things in memory, like the libraries, but also the location of the heap and the stack, are randomized every time you launch the application. And DEP means that you cannot just add new code to the application. If you send some message, then that will be handled as data, and data cannot be executed by the application. And how these mitigations are often bypassed is by, or in the case of ASLR, is by finding an information leak. This means that you can read something from memory somewhere, and using that you can infer where the library that you need is in memory, or the other data that you need. That's also something we used. But the vulnerability we had is something that can write. So we had an operation that can write, but we need to use it to read. Now, how do we do that? It's kind of like asking somebody to read a book using a pencil. Now, for that, we combined it with that first additional vulnerability, the HTTP connection. We wanted to leak an address from one of the OpenSSL libraries, and exactly why I'll get to later. We had decided we wanted an address from libcrypto. And if we wanted to leak something, then it had to be from an object that would be in the same bucket as we used. Now the bucket is 1025 to 1088 bytes in size. And we also needed a way to get that back to us. And as I said, all the XML goes through the server. So if you copy some binary data and then try to send that into an XMPP packet, then the server will see, well, this is not valid XML. I'm not going to send this. So we needed to find a trick to make sure that we could obtain this information, which is just exactly why we wanted to use that HTTP connection. Now, in the OpenSSL source, I found this TLS1 PRFP key context object. This object, there are a couple of these created every time a new handshake happens on TLS 1.0 up to TLS 1.2. And they're also very shortly lived. So they are created, used, and then deallocated in just one function call. And it contains a pointer to a struct from libcrypto at the first offset, so place 0. And importantly, that offset is not erased when the object is deallocated. So here is the full definition of this object. So the EVP-MD is a pointer to, again, libcrypto. So this is the information we wanted to obtain. Now it does, when you erase this object, then the seed is cleared because that's sensitive data, but the MD field was not erased. So this meant we could follow the following plan. We used that HTTPS connection vulnerability to set up 2 connections to a server under our control. On the first connection, we close it immediately after the handshake. This would ensure that there are a couple of those TLS PRF context objects still in memory, although they are freed. On the second connection, we make sure that we can request a URL with a path of 1025 bytes, or basically anything between 1025 and 1088 would work. And then we would use our buffer overflow to overwrite the null byte at the end of that path in the memory. And then we would complete that second connection. And then, because it would keep reading after that missing null byte, it would send some extra data from memory back to us. So here's that URL we could trigger a connection for. Now, how this is stored while it is waiting for that connection to happen is like this. So this is how C often handles text. There's a 0 byte which indicates that it ends there. So if you want to read something text-like from memory, then you just keep reading until you find that 0 byte, and then you know you're at the end. And then here in yellow, you see that pointer that we wanted to obtain. Now, if we trigger the buffer overflow, and we make sure that we overwrite everything exactly up to that 0, not everything after, because we want to obtain that. And then we continue the connection, then it will use this as the path and keep reading into that other object in memory. So we could use this to leak the address or this pointer from memory and send it back to us. Now, the first time I did this, it worked once, and then it didn't work again for 2 days. And then it worked again. It took another day before it to work again. So we had to make sure that the odds for this working would get from 3 days back to 3 minutes. And we used a couple of different tricks for that. We set up multiple connections to both web servers. So there's multiple things waiting to download. And also, because it happens during a handshake, what we found is that if you renegotiate a connection, so this is a feature in TLS where you can basically do a handshake again on an existing connection. And if you do that, then these objects are again created and deallocated. So if you keep doing this in a loop, and OpenSSL considers that fine if you keep doing that forever, then the buckets will keep being filled up with these freed objects containing used TLS PRF key context objects. And we could also overflow multiple times, of course, to increase the chance that we overwrite the correct path. Now, normally, if you want to exploit a heap vulnerability with some randomness, you can just create more and more and more objects to make sure that the chance of success is as high as possible. But for us, this didn't really work. We needed to find a good balance because our exploit required 3 objects to be in line, where the third one is actually deallocated memory. So we couldn't just fill up everything with the paths because then there would no longer be any of those free objects. And we treat this for days leading up to the competition to get this as reliable as possible, combining with making the heap grooming as reliable. And the path after this, the parts after this are way more reliable than up to this point. So you can also see here that these mitigations really do make our exploit a lot more work and also a lot harder to make reliable. Now, the third step is actually hijacking the control flow, so making the application executing something other than what it intended to execute. So this is not yet new code, but this is just trying to divert it to some other code within the application. So for this, we were looking for a function pointer, which gets called, and in an object that we can override. It could also be a vtable pointer, so this is something C++ uses, if a function in the vtable gets called. And again, it needs to be within the size of our bucket. Now, what a vtable is it's used for virtual functions in C++. And it's basically a list of function pointers that can be called. So we had to find an object of that size containing a vtable. But also, if you override the vtable, if you override the function pointer, then you can directly point it to somewhere else. But if you override the vtable, then that vtable needs to point to something which then points to the function you want to call. So there's another indirection step there. So we need to make sure that there's a vtable and we know the address of that vtable. And then also we need to make sure that the vtable is actually used, of course. Now, how we use this is the second additional vulnerability I described. So those GIPHY files that we could send to a user. So we could put a fake vtable into a GIF file and then repeat the same data in it such that the file is eventually 25 megabytes. And then if we send that same file to the user 20 times, it means that it doesn't need to download it 20 times. It just downloads it once, but it still does allocate it in memory 20 times. Now, in a 32-bit application on a Windows, we have 2 gigabytes of RAM available. This means that if you send this 25 megabyte image 20 times, that a large part of the memory space will be filled with the image that we sent, about a quarter. And then we could reliably guess some address that would fit within those GIPHYs. So this image tries to demonstrate that. Now, the first ones we don't really know yet because there's still some randomization there. There may be other images that the user has recently downloaded. So the first ones we're not sure where they are. But if you send enough of them, then eventually it has to start filling up the space sequentially. And then this becomes a predictable pattern that we can then use to guess where the image is. So to override the vtable, we had to find an object that would fit into the correct bucket. And for that, we used the sound of the video you just saw. So if you are being called on Zoom, then it will start playing this ringtone. And what we noticed is that to do this, it creates a file wrapper object. And that object fits nicely within our bucket. And it contains a vtable. And every time that sound loops, it opens the file, reads it to play it, and then closes it again. And in the next loop, it does the same thing again. So we also noticed that the vtable contains that close function that is being used for closing that file again. So if we overrode one of those file wrapper objects, then as soon as the sound stopped playing and it would close the file, it would start executing code that we injected there. And then the next step is to actually execute our own code, so gaining the remote code execution. Now, to describe how this works, I'll first need to describe control flow guard. This is another mechanism for preventing exploitation. And it's to prevent return-oriented programming. So return-oriented programming is a method which is often used in exploits to combine together different parts of the application. And so control flow guard attempts to make this harder or impossible. So how it works is, if there's a call to a function pointer, then the compiler inserts a check, which at runtime will check if that location of that function is a known start address of a function. So what this means is that you can no longer execute just the last few bytes of a function. You really need to execute it completely, otherwise control flow guard will crash the application. Now, we had basically 2 ways to get around this. The first we looked at for a short time, but eventually gave up on it. And that's just calling an existing function that you could use. So we considered loading a malicious DLL, but this didn't really work, so we gave up on this. Or the second option was to find a library that is not compiled with control flow guard. Like, we want to leak an address from libcrypto, because not being compiled with control flow guard means actually two things. So first of all, those dynamic checks are not inserted. So from libcrypto, we can call any address. But more importantly for us, any dynamic function call from any of the libraries which do use control flow guard, but where the target function is in libcrypto, those are allowed. And the reason for this is that the compiler has to inject some information about where valid start addresses are for each library. And because libcrypto is not compiled with this, it just allows anything. So for this, we formulated the following plan. We use the stack pivot gadget from libcrypto. What this means is that we can replace the stack and then we can use that stack to perform a ROP attack. So this return-oriented programming, we use that to mark some part of the file that we already placed in memory as executable. But we were limited to the addresses from libcrypto. So it's still a pretty large library. So we have a lot of gadgets and functions there. We're also limited in what functions are important by libcrypto, because we only have the address from libcrypto. Any other libraries we do not know, except if they are imported by libcrypto. And then we can jump to the code that we included in the GIF file to execute it. Now, our ROP stack, I'll not go into full detail, but I'll try to give a slight explanation of how it worked. You could call get module handle to get a handle to the kernel 32.dll, which is one of the imported functions. And then we would save that returning address. And then we could call get proc address. So what this function does is you give it a string and then it returns the address and memory of that function. And we could use this to look up the address of virtual protect. So virtual protect here is the function we want to call, but we didn't have the address imported. But by using get proc address with get module handle w, we could look it up dynamically and then call it. And by calling it, we can make our own code executable. And then we could jump to it and execute. So here we have a demonstration of the attack, how it worked. On the left, there's a virtual machine running Windows. And first, we will demonstrate that it is actually the latest version of Zoom at the time. And then we will start our exploit here. Now, first, it will do some steps that I didn't describe, but they're basically just part of the grooming of the heap. And what it will do now is it will start sending those messages for heap grooming. It's fast forwarded a little bit because it's quite boring and there's not much happening here. And now it revokes those messages again to clear that room as in the previous video. And now it starts making those connections to try to leak that object. And in this case, we were quite lucky because it actually took only 2 loops to leak the address. Sometimes it could take dozens of loops for it to work, sometimes just the first one. And in this case, you see here the information leak obtained, and it got the address of libcrypto. Now it's uploading that image, or actually waiting some time to allow the client to download the image. And then in this case, we were also quite lucky. Sadly, it doesn't have sound in this case, but if it had, then there would be just 1 loop of the sound playing. And as you can see now, that already triggered the buffer overflow. And then we got a reverse shell and we start calculator to show that we can start any application. As you can see, we can now execute code as that user. So how did it go during the competition? Well, before the competition started, we thought we had about 50–60% reliability. So it's not great, it's not fantastic. But if you have 3 attempts, then we thought, well, it's good enough. If you watch the stream, you already noticed, but the first attempt failed during the information leak step. And then for some reason, we're not quite sure, but resetting it took a while. So basically what they had to do is they had to shut down the client, start it, clear all of the chat messages because those might influence the heap. shut it down again, and then start it again. But for some reason, we're not quite sure, this took a while. And then we could start our second attempt, but there was so little time left on the clock. It was quite clear that we're not going to have a third attempt. But luckily, with just 20 seconds remaining, that second attempt succeeded. And then how this competition works is that after you demonstrated the vulnerability, you have to go into a call with the developers. So we had a Zoom call with Zoom to discuss the vulnerability in Zoom. And then what they do is they look up if they already know about this vulnerability. And they confirmed that they didn't know about any of the 3 vulnerabilities we used, which meant that we won. And how this competition works is that you also get the laptop that you hacked, which is now standing behind me. And we got the Master of Pawn title because of points are assigned. They rewarded us with a jacket. Now, if you want to learn more, or if I went a bit too fast, we wrote a very long, very technical write-up that you can find on our website. There's a link here. And if you use Zoom, then please don't forget to update if you haven't in the past 6 months, so you can keep sharing those company secrets online safely. Now, please enjoy the rest of the conference, and if you have any questions, feel free to reach out to us.